Hello everyone, my name is Emmanuel Ochoa, and today I'll be presenting on screw chillers. We'll go over what they are, how they work, the main components, and how they're used in real-world applications. To start, let's understand what a chiller is. A chiller is a system that removes heat from a liquid, usually using vapor compression or absorption cycles. This cooled liquid is then used in processes or to cool air and HVAC systems. To give you a clearer picture, I have a short video that explains this in more detail.
You hear the term chiller thrown around plenty, and you have to ask yourself the question at some point, what really defines a chiller from just a regular air conditioner? Like why is it special? What is that? The short answer is it's a hydronic cooling machine, meaning the evaporator itself uses a hydronic evaporator. Now, hydronic is using water. That is, hydro is the use of water through the evaporator, and we're going to cool the water down to go cool the space. But a chiller specifically, whether it be water or brine or a glycol solution, either way, it's a fluid. We're cooling a fluid versus air. So a regular air conditioner, we're processing air over a coil, an air over coil, and then we're cooling and removing the heat from that air and to relocate it outside. Well, the chiller has a evaporator that moves the water instead. So if you are processing water, you have a chiller. Now, you can still have air cooled and water cooled chillers, and that's where the condenser itself, whether or not it's using air for air over condensers, a regular split system, for example, that's an air over condenser, it's air cooled, or whether we have a water cooled that we're moving water throughout the condenser barrel. So a water source heat pump or a big centrifugal chiller is maybe something that comes to mind for you. Those are water cooled systems. So, and just that's your basic definition on what a chiller is. And we'll dive more into in future videos just why.
Now that we know what a chiller is, let's talk about the screw compressor, which is at the heart of the screw chiller. A screw compressor uses two interlocking helical rotors to compress refrigerant gas. It operates smoothly, is quieter, and is more reliable than other types of compressors, like reciprocating compressors. Let's take a quick look at this next video, which explains how screw compressors work.
MAN Diesel and Turbo manufactures tailor-made process gas screw compressors for customers, a modular system of tried and tested components guaranteeing the utmost reliability. Depending on its size, a compressor stage can suck in and then compress volume flows of between about 200 and 100,000 cubic meters per hour. All screw compressors operate according to the basic principle of a positive displacement machine, whose key element is a pair of spiral rotors. During operation, the rotors turn and the spiral teeth mesh together, forming chambers between the rotors and the casing wall. Rotation causes the chambers to move from the suction or intake side to the compression or discharge side. These chambers are connected to the suction nozzle via ports. As the chambers enlarge, they are filled with gas flowing in through the nozzle. To understand the compression process better, let's look at an individual chamber. It enlarges, is filled with gas, and then closed by a circumferential edge in the casing. The rotors now transport the gas to the discharge side, where the chamber shrinks and the retained gas is compressed. Let's view the process again, this time from below. Once the gas is compressed, the chamber reaches another port connected to a discharge nozzle, and the gas flows out. In fact, all the chambers between the two rotors are being filled and emptied continuously. This means that with a screw compressor, the compression process is more or less ongoing. The design of a screw compressor combines the advantages of a positive displacement machine with those of a rotating machine, making this type of compressor suitable for a very wide range of applications and process gases.
When you combine a screw compressor with a chiller system, you get a screw chiller. Screw chillers are popular in both HVAC and industrial systems for cooling water or water glycol mixtures. The main components include the screw compressor, evaporator, condenser, expansion valve, and the refrigerant loop that connects all these parts. Let's break these down. The screw compressor handles large cooling loads efficiently. The evaporator is where chilled water absorbs heat. The condenser rejects heat to the environment. The expansion valve drops refrigerant pressure before it returns to the evaporator. Controls and sensors monitor system health and performance. The screw compressor itself has fewer moving parts, which increases reliability. Using male and female rotors, it compresses refrigerant smoothly and continuously, providing quiet operation, which is great for long-term use. The vapor compression cycle is the core of chiller operation. Refrigerant circulates and changes phases to move heat. There are 4 main stages. The first being evaporation. The refrigerant absorbs heat and evaporates. Next is compression. Vapor enters the screw compressor, raising pressure and temperature. Then condensation. The vapor releases heat and condenses back to a liquid. Then lastly, expansion. The liquid refrigerant expands, lowering pressure before it repeats the cycle. Now, let's take a closer look at these two diagrams, the TS and PH diagrams, which help us visualize the vapor compression refrigeration cycle used in screw chillers. Starting with the TS diagram, which stands for temperature entropy, this graph shows how the temperature of the refrigerant changes as it moves through the cycle, while also tracking entropy, which basically represents the disorder or energy dispersal in the system. At the beginning of the cycle, we have low temperature and low entropy in the evaporator. As heat is absorbed, the refrigerant evaporates, moving across the graph toward higher entropy. Then, in the compression stage, the refrigerant's temperature rises sharply as it is pressurized by the screw compressor, which is shown by the steep upward line. Next, in the condenser, the refrigerant releases heat to the surroundings, which brings the temperature down while maintaining high entropy. Finally, it passes through the expansion valve, rapidly dropping in both temperature and pressure, and returns to the evaporator to repeat the cycle. Now, if we look at the pH diagram, which shows pressure versus enthalpy, this gives us a great view of the energy balance in the system. We start at low pressure and low enthalpy in the evaporator. As heat is absorbed, enthalpy increases until the refrigerant becomes a saturated vapor. When the vapor enters the compressor, we see a steep rise in pressure and enthalpy. This represents the work done by the screw compressor. In the condenser, the refrigerant rejects heat to the environment, causing enthalpy to decrease while maintaining high pressure. Finally, during expansion, the pressure drops sharply and the refrigerant returns to its starting point, ready to absorb heat again. Both of these diagrams are valuable because they help engineers analyze efficiency and performance at every stage of the cycle. They also help understand how temperature, pressure, and energy all interact inside the system, and how the screw chiller maintains efficiency under varying loads. So, these visual tools not only guide system design, but also help diagnose performance issues in real-world applications like HVAC systems or industrial cooling. There are 2 main types: air-cooled, which uses ambient air to reject heat. It's easier to install and maintain. And water-cooled, which uses a cooling tower and water loop. It's more efficient and better suited for larger buildings. Screw chillers are commonly found in large commercial HVAC systems like malls and hospitals, industrial processes and manufacturing plants, data centers, food processing, and cold storage facilities. Advantages include high efficiency at both part and full load, low maintenance, quiet operation, and compact design. However, they do have a higher upfront cost and require skilled maintenance for optimal performance. Screw chillers are excellent for high lift situations, meaning they can handle significant temperature differences between the evaporator and condenser while maintaining efficiency. They also support energy recovery systems. Screw chillers can reject heat at around 120 to 140 degrees Fahrenheit, which is great for domestic hot water and hydronic heating systems. A perfect example is a hospital. Hospitals have constant cooling demands, require quiet operations, and need highly reliable systems. Screw chillers are ideal because they efficiently handle varying loads. That wraps up my presentation on screw chillers. Thank you for your attention. I'd be happy to answer any questions.